Let us start with lecture number 30th of this course. Now we are discussing the working principle of neurophagy system, and in the last class we discussed how to design and develop the neurophagy system based on Mamdani approach, and today I will be discussing how to develop the neurophagy system based on Takagi and Sugeno's approach. Now, Takagi and Sugeno's approach, all of you have studied and you have understood. So, today I'm just going to discuss how to represent the fuzzy reasoning tool based on Takagi and Sugeno's approach using the structure of a neural network so that we can train that fuzzy reasoning tool with the help of an optimizer and some known input-output data. Now, this neurophagy system based on Takagi and Sugeno's approach, this is very popularly known as adaptive neurophagy inference system. In short, this is popularly known as ANFIS. So, adaptive neurophagy inference system, that is ANFIS, is very popular. As I mentioned in the last class, that if you just give the Google search for this paper related to ANFIS, you'll be getting a very large number of papers. Now, the first concept of ANFIS that was proposed by Zhang and in the year 1993. And after that, so this particular ANFIS has been modified in a number of ways. Now, the ANFIS which I am going to discuss is actually the initial version or the original version, okay, proposed by Zhang. And as I told, after that it has been modified in a number of ways. Now, in Takagi and Sugeno's approach, all of you know that we use membership function distribution only for the inputs, but for the output variable, we do not use or we need not use any membership function distribution. What is the reason? Reason is very simple, because in Takagi and Sugeno's approach, the output of a rule that is represented as the function of the input variable. Okay. Now, let me take a very simple example of a process having two inputs I1 and I2 and only one output, that is O. Now, supposing that this is the membership function distribution for the input I1, okay, and the input I1 has been expressed, say, using three linguistic terms, that is low, medium, and high. And for simplicity, I'm considering the triangular membership function distribution. Similarly, for I2, the second input, once again, I'm using three linguistic terms like your small, large, and very large to represent the I2. Now, as I told, that to represent the output, no membership function distribution is required in Takagi and Sugeno's approach. Okay. And according to first order Takagi and Sugeno's approach, the output of the ith rule is nothing but the linear function of the inputs, that is nothing but yi is your ai multiplied by I1 plus bi multiplied by I2 plus ci. I varies from 1 to up to 9. Now we are considering three linguistic terms for I1 and three other linguistic terms for I2. So what is the maximum number of rule? The maximum number of rule becomes equal to 3 multiplied by 3, that is 9. That is why I varies from 1 to up to 9. And these AI, BI, CI are the coefficients of the rules. Now for the first rule, the values of the coefficient will be something, and for the second rule, the values of the coefficient will be something else. Okay, so for each of the 9 rules, we have got a separate set of coefficients. Okay, so this is how to represent the rule according to Takagi and Sugeno's model. Now this is the ANFIS, that is the Adaptive Neurophagy Inference System. Don't think that this is a very complex. Look-wise, it may seem it is very complex, but it is in fact very simple. I'm just going to make it very simple. Okay. Now listen to me very carefully. Now let me repeat once again. I'm modeling a process having two inputs I1 and I2, and there is only one output, that is O. Okay. Now to represent the I1 and I2, we use some membership function distribution, the way I did in the last class. So for I1, I am using three linguistic terms: low, medium, and high. Similarly, for I2, it is small, large, and very large. Okay, and for simplicity, I have considered like triangular membership function distribution. Now, this ANFIS architecture consists of 6 layers, and you know the purpose. The purpose is to represent Takagi and Sugeno's approach of fuzzy reasoning tool using the structure of a neural network so that I can train it very easily. Okay. So first layer is the input layer, and generally we use some linear transfer function. So output of the first layer will become equal to its corresponding input. Okay. And here there will be membership function distribution denoted by this connecting weight, that is V11, V12, and V13. And to maintain symmetricity in the membership function distribution, so we are going to follow the same principle which I discussed in the last class. That is we try to find out the average of these three connecting weights. Okay, so V1 average we try to find out, that is nothing but V11 plus V12 plus V13 divided by 3. Similarly, the average weight corresponding to the second input, that is I2, and this V2 average is nothing but V24 plus V25 plus V26 divided by 3. Okay, so I can find out the membership function distribution, symmetric membership function distribution for I1 and I2. Okay, and the second layer is nothing but the fuzzification layer. The moment the inputs are entering through the membership function distribution, so we'll be getting the value of membership as the output. So output of the second layer can be determined very easily. Now layer 3 actually denotes all nine rules. Okay, so there are 3 linguistic terms for I1, 3 other linguistic terms for I2. So 3 multiplied by 3. So there are 9 rules. Okay, so there are 9 rules, and on layer 3, you can see there are 9 such neurons. Okay, you can see that denoted by the circles. Each neuron is going to represent one set of input parameters. So as input to the third layer, you'll be getting 2 such membership function value. One is corresponding to I1, another is corresponding to I2. And in Takagi and Sugeno's approach, if you remember, we multiply the membership function values. Okay, so the output of layer 3 is what? That is the multiplication of these two input membership values. Okay, and here you'll be getting this particular output. So for each of these particular things, particular the fired rules, you'll be getting your non-zero, your this thing non-zero, that is called the firing strength, denoted by W. So you'll be getting W1, W2 up to W9. And if there is no such firing, what will happen to the W? W will become equals to 0. Okay. Now, whatever W values we are getting as output of layer 3, those things will go to layer 4. And our purpose is to find out the normalized value of the firing state. Okay, so we try to find out what is W1 bar, W2 bar, W3 bar up to your W9 bar. So we try to find out your the normalized values for this particular the firing state. And once you've got the normalized values for this particular firing state, now what you do is we try to find out the output of the fired rule. Okay, supposing that for the first rule, the output is your y1, second rule it is y2, third rule it is y3, and so on. So if there is non-fired rule, what will happen to the output? We need not calculate the output. And your this particular W bar corresponding to the rule which is not fired at all, that will become equal to 0. Now, there are 9 such rules, but at a time, a maximum of 2 multiplied by 2, that is 4 rules will be getting fired. Okay. So if it is fired, so I'll be getting non-zero W1 values and non-zero Y. And here in this particular layer, actually what we do is on layer 5, so we try to find out what is the multiplied form of W bar and Y bar. So we multiply the firing strength with the corresponding output of the fired rule. That particular numerical value we are going to calculate as the output of layer 5. Okay, and all such non-zero outputs are summed up here in layer 6, and ultimately you'll be getting the output of that particular the output of that particular system. Okay, so I'll be getting this particular output, and once we get this particular output, okay, now it will be compared to the target output to find out if there is any deviation. And as you know, deviation could be either positive or negative. So we take the mod value, and after taking the mod value, we try to find out the average. And that particular average will be the fitness of your the GST, particularly if you use a genetic algorithm to find out the optimal design of this particular the NFIS. Now, if you want to use a genetic algorithm, or if you want to optimize with the help of the backpropagation algorithm, what should be the design variables? The design variables are very simple to identify. The performance of this particular NFIS will depend on definitely the membership function distribution of the input variable, and that is denoted by your these connecting weights. Okay, so these connecting weights, okay, you can consider as the design variables, and for simplicity we consider the average because we want to consider the symmetric membership function distribution. So there will be one design variable here, that is nothing but V1 average. Okay. There will be another design variable here, that is V2 average. Okay. And there will be a few other design variables. What are those? Those are nothing but the coefficient of the rule, that is AI, BI, and CI. Okay, you can see that I've taken, see, please concentrate on this particular line. From 1, I have taken up to this, and you see it is entering everywhere on layer 5. Similarly, from I2, I've drawn one line, okay, and I'm taking the input from this I2 and I'm passing it to layer 5. Are you getting my point? So what does it mean? It means that I'm considering y, and to determine the y, I'm going to use the coefficient of the transfer function, the coefficient of the rules, that is ai, bi, and ci. Okay, so ai, bi, ci, these are all design variables. Now, if there are 9 such rules, for each rule there are 3 such coefficients, A, B, and C. So 3 multiplied by 9, there will be 27 variables this side, and here there will be one more variable 28, another variable 29. So if you want to represent, so this particular n phase with the help of a GA string, I'll have to encode the information of 29 variables on the GA string. Okay, now I hope it is very clear to all of you that a particular GA string lying in the population of genetic algorithm is going to represent the NFIS architecture. Okay, all the details of the NFIS. Now you pass all the known training scenarios one after another, and you store how much is the average deviation. That is nothing but the fitness. Okay, so for the whole population of the genetic algorithm, you'll be getting the fitness information, and after that, GA is going to use its own operator like reproduction, crossover, and mutation, and through a large number of iterations. So GA is going to find out what could be the optimal NFIS architecture. And as I told that as GA is a population-based approach, there is a possibility you'll be getting multiple optimal solutions. Okay, that possibility is there. So I hope this particular idea is clear to all of you. Now, before I go to the numerical example, another thing I want to mention. Now, if you look into this particular architecture very carefully, see, very purposefully, I have used two types of symbols to represent the neurons. Have you seen that? Now, on the second layer, I'm using square, not circle. Okay. On the fifth layer, I'm using square, not circle. But on the first layer, third layer, and fourth layer, I've used circles. So, what is the reason? Why am I not using all circles or all your squares? Why am I using a combination of squares and circles? Okay, answer is very simple. The moment I'm using the squares to represent the neuron, there is a chance of further improvement. This indicates that if I use an optimizer, optimizer is going to do some modification. Okay, here only on layer 2 and your layer 5. Layer 2 means what? That is the distribution of membership function for the inputs I1 and I2. What is what do you mean by layer 5 variables? That is nothing but the coefficients of rules, that is your AI, BI, and CI. So I hope I'm clear to all of you, like how to represent. So this particular NFIS architecture inside the GA string, and GA will try to evolve using the batch mode of training, like the optimal or the near optimal NFIS architecture. Now, as I told that out of these particular 9 rules at a time, a maximum of 4 rules will be fired. Now, supposing that these 4 rules are going to be fired, the fired rules are as follows. If I1 is low and I2 is small, then Y1 equals to A1 I1 plus B1 I2 plus C1. And this is the Takagi and Sugane's approach, and very purposefully. See, I've not used AND operator. I've used conjunction AND. Have you seen that? So this is small a n d, but not capital A N D. Okay. Second fired rule is this. Third fired rule is this. and the fourth fired rule is this. Okay. Now, whatever I discussed, same thing I have written it here. Layer 1 output is nothing but the input because we are using linear transfer function. Layer 2 is the fuzzification layer. Layer 3, we try to find out the firing strength of the rules. So we simply multiply the mu values. Okay, mu corresponding to I1 and mu corresponding to I2. And we get the other firing strength like W2, W4, W5, etc. Then we calculate the normalized firing strength, that is nothing but W1 bar is equals to W1 divided by W1 plus W2 plus W4 plus W5. Okay. Similarly, we get W2 bar, W4 bar, and W5 bar. Okay. And layer 5, we try to find out the output, that is nothing but the output of the first neuron lying on the fifth layer is nothing but W1 bar multiplied by Y1. 5O2, that is the output of the second neuron lying on the fifth layer is W2 bar multiplied by Y2. And output of the fourth layer lying on the fifth output of the fourth neuron lying on the fifth layer is W4 bar into Y4. Then output of the fifth neuron lying on the fifth layer is nothing but W5 bar into Y5. And in layer 6, we try to find out the overall output and we just sum them up. You'll be getting the output of the neuron lying on the sixth layer. Okay. And here I have put a note which I have already discussed that the performance depends on membership function distribution of input variables and the coefficients AI, BI, and CI. Now to train, if I use your the back propagation algorithm, that will be back propagation trained neurophagy system. That is the back propagation trained NP sort of thing. And if I use a genetic algorithm, okay, for the tuning of NPs, that will come under the umbrella of genetic neurophagy system. Okay. So I hope it is clear to all of you the working principle of this particular the NPs. Now, based on whatever I have discussed, I'm just going to solve a very simple numerical example and which I have designed very simple one so that we can understand more clearly the working principle of NPs. The numerical example which I have designed is as follows. So I'm just going to design one NFIS to model two inputs I1 and I2 and one output that is O. Okay. And to represent I1, I'm using only two linguistic terms for simplicity, that is low and high. And to represent I2, I'm using two other linguistic terms, that is small and large. So there are two linguistic terms for I1, two other linguistic terms for I2. So 2 multiplied by 2, there will be 4 rules on layer 3. Okay. So here we try to find out the firing strength, the normalized value of the firing strength, the outputs of the fired rules, then the final output. Okay. So this is a very simple network I have designed. These are the membership function distribution for I1 and I2, and the design variables are denoted by D1 and here it is D2. For simplicity, we have considered two such right angle triangles whose base weight is denoted by D1 and here it is denoted by D2. Okay. Now D2 represents the base weight of small and large right angle triangle, and for simplicity we have assumed that V11 equals to V12, okay, and V23 is equals to V24, okay, and we'll assign some numerical value also, okay. Now there is a maximum of 4 fired rules, and according to Takagi and Sugeno's model, the output of the ith rule yi is nothing but ai1 plus bii2 plus ci. I varies from 1 to 3, 4, and ai, bi, ci are the coefficient of the rule. Okay. Now this table shows the values of the coefficients for different rules, rule 1, 2, 3, and 4. These are the values for AI, BI, and CI. Okay, just a minute. I have got a phone call. Let me. Hello. हाँ ठीक. हाँ. You send it to our mechanical engineering department. Okay, let it be there in any office. I am taking a class now. Okay, after that I'll be coming to the department, and you collect it in the afternoon. Okay, you collect it from mechanical engineering department. Okay, afternoon. I see. I'll be going after taking the class. So by one you'll be getting it. I'll put my signature. You keep it in the mechanical engineering department office. Okay. Ha. Oh, thank you. Sorry. So the range for this D, that is D1, D2. So D1 is varying from 0.8 to 1.5, and D2 is varying from 4 to 6. Okay. Now assume the normalized weight values as follows. So we are going to consider V11 equals to V12 equals to 0.3. Then V23 equals to V24 is 0.5, and determine the deviation in prediction for the trading scenario. So what we are going to do, we are going to pass I1 equals to 1.1, I2 equals to 6.0, and target output is your 2.3. Okay, so let us see how to find out the deviation in prediction. Now the solution, the way we discussed in the last class, so we can find out the real value corresponding to this particular, the normalized value using this expression, x equals to n multiplied by x max minus x min plus x min. Now using the above relationship, d1 is nothing but 0.3. That 0.3 is the normalized value multiplied by the range. X max is 1.5, x mean is 0.8 plus 0.8, so 1.01. Similarly, D2 is 0.5 multiplied by 6.0 minus 4.0 plus 4.0, that is nothing but 5.0. Okay, so you'll be getting this particular D1 and D2. Okay, and once you've got this particular D1 and D2, now you can draw the modified membership function distribution for the two input variables. Okay, that is I1 and I2. So layer 1 output is nothing but the input because linear transfer function. Okay, layer 2 will be getting the membership function distribution. Okay, for example, say corresponding to I1, we can find out mu low is 0.900990. Then mu h corresponding to I1 is 0.099009. Similarly, corresponding to I2, I'll be getting mu sm is 0.8 and mu lr is 0.2. Then layer 3, So we are going to collect the membership function values for each of the fired rules. Okay. Then we are going to multiply and you'll be getting the output. So we multiply the corresponding mu values. Okay. So we can find out the firing strength W1. Similarly, you can find out the firing strength W2, W3, and W4. Okay. The normalized firing strength is nothing but W bar, that is W1 divided by the sum of all W values, that is W1 bar. Similarly, W2 bar is W2 divided by the sum of all W values. Then comes your W3 bar, W4 bar, you can find out. And layer 5, we can determine the output of each of the 5 rules, that is Y1, Y2, Y3, and Y4. Then we can find out the output of the 5th layer, something like this. Okay. Then we sum them up to find out the final output, that is the output of layer 6. So this is the calculated output 2.255860, and the target output is your 2.3, and you'll be getting the deviation. And as you are getting the deviation, now I'm just going to pass the second training scenario, third training scenario, all the training scenario, then find out the average. That particular average will be the fitness of the GA. So I hope you have understood the working principle of this particular, the NFIS. Okay. Yes. So we have used the principle of neurophagy system, both Mamdani approach as well as Takagi and Sugenda's approach, and some numerical examples have been solved. Okay. So I have finished discussing the principle of NFIS. And now if you have any doubt, you can ask me. So now it is open to discussion. If you have any doubt, please ask me. Yes, any doubt on NFIS? Any doubt? Okay, good, very good. So all of you have understood. Okay. Now with this, let me conclude the syllabus of soft computing, that is the UG course. Okay. So for the UG course, that is the soft computing MF 41601, today's class is the officially last class. Okay. But in tomorrow's class, I'm just going to discuss some other topic, some additional topic, and that is compulsory for the knowledge-based systems in engineering. But for the students of soft computing, this is optional. It is up to you. If you want to know, you can join. It is up to you, but it will remain compulsory for the students of knowledge-based system. Okay. So tomorrow is Friday. As usual, we are going to meet at 9 in the morning. Okay. And this class will be compulsory for knowledge-based systems, but it is optional for your the soft computing students. Now, regarding your test, I've already sent, I think last evening I sent a mail to all of you separately for the knowledge-based system and soft computing regarding your third and last test. Okay. And there will be another thing, another small assignment will be there. And for that particular assignment, I'm going to give only 2-3 days time. It is very simple. No numerical example, nothing, no calculation. Based on your understanding for the whole class. Okay. So I have designed two problems. It's not the numerical example sort of problem. These two problems are different for the students of soft computing and knowledge-based system. Okay. So might be by the end of this week, I'll be sending that assignment and I'll give you only 2, 3 days time because it will not take more than half an hour or 40 minutes if you have attended all my lectures and if you have understood little bit, so you'll be able to write. Okay, it's very simple and I'll give you necessary instruction also. The answer for that assignment might be within 50 words, 60 words, not more than 100 words. That type of assignment. Okay. And but that will be very interesting and that will test your understanding of this particular the subject. Accordingly, I'll be designing the two problems. Okay. So that will be the last assignment and your third test or the last test, the date also I have announced. Okay. So after that, your grading, I'm going to start your grading. Okay. Now, regarding the students who have missed anything like assignment, test, or whatever may be, okay, I'm requesting you to send a mail to my Gmail account, that is softcomputinglab@gmail.com, not softcomputingcourses2020. Okay, if you have, now this is only for that. If you have missed any assignment or if you have missed any test, if you need some advice from me, okay, you can send mail. Okay, by this uh, mm, Saturday, you should send the mail. Okay, to my softcomputinglab@gmail.com, and let me think like how can I help you. Okay, so that I'm going to think. For example, say if some student was absent due to some medical problem, okay, in some test, whether I can take a viva sort of thing or that type of thing, that I'll have to find out. Okay, so I'll give you the opportunity. Okay, now regarding the students of soft computing, let me just give my concluding remarks as follows. Like I've tried my level best, uh, although there are many such functional constraints, to give you some idea regarding the principles of soft computing. And I hope I'm able to give you some sort of initial momentum which is required to start learning this particular the subject. Okay. And in this particular subject and in each of the tools, there are many research issues. Fundamentals I have discussed, little bit of research issues also I have tried my level best to discuss. Okay, but there are many such research issues. Many things are unknown till today. Okay, so there is enough scope for doing research in the field of soft computing. If somebody wants, if anybody wants, he or she can spend the whole life in doing research in the field of soft computing. It is such a huge, and your like your space or the scope is such a huge. Okay, so I hope with the initial momentum which I could give you a little bit, okay, you'll start moving so that you can work in the field of soft computing, either developing the fundamental tools, applications, or whatever may be. I hope at least some of you will be thinking in future to build career in the field of soft computing. So with this, I'm just going to stop today, and tomorrow's class will be as usual for the knowledge-based systems in engineering. But as I told, students of soft computing may also join tomorrow's class, but that will be optional. Okay, so let me stop here today, and I wish all the best to the soft computing students because officially this is the last class of the soft computing course, that is the UG course. And for the soft computing course, that is the UG course, test will be held on 11. And for the knowledge based system, as I told, that will be on 13. But for the knowledge based system, students, there will be a few more classes. Okay.
Sir,
So let me stop here. Please.
so what would be the topics you would be covering in the only knowledge-based system classes, like which are optional for soft computing students?
I'll have to think, okay, but a few topics which are coming to my mind, okay, but I have not yet taken the final decision. There are many other topics, okay, so much time is also not there. At least a few things I'm planning to discuss, like the principle of particle swarm optimization, another very popular nature-inspired optimization tool. Then principle of simulated annealing is another very popular non-traditional tool for optimization. Might be some topics related to scheduling or scheduling genetic algorithm. uh, So that is another class of optimization problem, like how to determine the optimal timetable for the institute. It's very difficult. I know the difficulty because I was professor in charge for the whole institute for 4 years. Professor in charge of timetable for our whole institute. So I know how much difficult it is. It is not an ordinary optimization problem. It is a special type of optimization problem, and that requires lot of modification on the GA operators. That I'll be discussing. Okay. If time permits, I may discuss a little bit on some other neural networks if time permits, like your uh, back propagation neural network I've discussed, recurrent I've discussed, but feed forward network I have not yet discussed to all of you. So if time permits, I may also discuss feed forward network. Okay, let us see the time. Okay,
Excuse me, sir.
please, please.
Sir, some of the final year students like have their project submission due by 8th, and we have placement exams also, sir. So can you please send the assignment after 8th?
After 8. After 8, 8 is Sunday, no?
Yes, sir. Even
Okay,
Sunday
no
we have
problem.
placement exams. So
No
that's why.
problem. I'll be sending 9 on 9. Is it okay? Is it
Yes, sir.
okay?
Yes, sir. Yes, sir.
Ah, okay. 9th I'll be
Yes, sir,
sending.
that would be helpful. Yes.
Okay, definitely. I'll help you. I'll be sending on 9. Okay. Any other thing? Any other thing? Okay, then let me stop here today. All the best to soft computing students.
Thank you, sir.